We're going to talk about 10.1, which is the introduction, and 10.2, and then we'll have a separate lecture for 10.3 and 10.4. We're going to talk about correlation and regression. And what we're doing for correlation and regression is looking at how two variables, two quantitative variables, are related to each other. And so in other words, if one increases, how does the other one increase? If one decreases, how does the other decrease? The chapter problem in your textbook on page 529 has to do with footprint evidence and the height of a suspect. So in the late 1800s, there was an anthropologist who collected foot and height measurements and used them to develop a rule for estimating a person's height from their footprint length. You can read about it in your book. We're going to look at a very small sample of 5 individuals, and we're going to use this as we work through the chapter. The other thing that I want to mention is in previous versions of the course we spent a lot of time talking about how we calculate the statistics, and these statistics are not difficult to calculate, just that the calculations are extremely tedious. So we are not going to focus on hand calculations. We are going to focus on how we use our technology. In the lectures, I will show you how to use StatCrunch. Your book has very clear directions on how to use Excel to do the same thing. We need to build some vocabulary, and so we need to talk about 2 kinds of variables. Again, we're looking at the relationship between 2 variables measured on the same individual, and they both must be quantitative. The first one that we're going to talk about is the response variable, and the response variable actually measures the outcome of the study. It's what you're trying to predict. We call it the dependent variable because it depends on the other variable, and when we graph it along the y-axis of your graph, because we're going to use scatter plots to investigate this data. Then the other variable is the explanatory variable. It explains the influences on the response variable. It's what you look at first. Because it doesn't depend on anything else, it's called our independent variable. When we set up our data tables, it is our x variable, and when we use our scatter plot, we plot it along the x-axis. Now, it's important to realize that sometimes there's no distinction, and then you pick. Sometimes it's clear, sometimes it's not. Now we're going to focus on linear relationships basically because they're relatively easy to pick out. There are other forms of the relationships, and those are in section 10.6, and we will look at those briefly at the end of our last chapter 10 lecture. When we look at this relationship, we want to look at the direction. We might have a positive association, meaning as one value gets big, the other one gets big, or as one value is small, the other one is small. What happens with these is if we would graph this for a positive association, the graph looks like it goes uphill. So large x's are associated with large y's, small x's with small y's, so a positive association looks like it goes uphill. When we have a negative association, that's going to look like it goes downhill. So what that means is small x's are associated with large y's, small y's are associated with large x's. You can look at this if X was the age of a car and Y is the value. A new car is worth a lot. An older late model car is not worth as much. Negative association. As you know, in statistics we need to use numbers, and we are going to measure the strength and the direction of linear relationships using numbers. So what we do is we look at how closely a non-horizontal straight line fits the point of the scatter plot. If it's a horizontal straight line, then that tells us there's no linear relationship. But we want to see how close are our points to a straight line relationship. And what we do is we calculate the correlation coefficient when we do that. And a lot of times this is simply called the correlation, and the symbol that we use for this is R. Sometimes it's called Pearson's correlation coefficient or Pearson's moment of correlation, but we use the symbol R. And R measures the strength of the relationship. So the stronger the relationship, the larger the magnitude of R. And it measures the direction of the relationship. If we have a positive R, it's a positive relationship. A negative R, a negative relationship. So when I talk about the magnitude of R, what I'm talking about is how far from zero. There are some restrictions on the values of R. A perfect positive linear relationship has an R equal to a positive 1. A perfect negative linear relationship has an R of a negative 1. If there's no relationship, then R is 0. So in other words, R must be between a negative and positive 1 inclusive. So it can be a negative 1, it can be a positive 1. So you won't get an R of 27.3. That's not between a negative and a positive 1. Both variables must be quantitative, and sometimes when we do R's, there really is no distinction between the response and the explanatory variable. It's a good idea to set them up at this point, but if you choose them the wrong way around, that's not a big deal because the value of R does not change when those variables are switched. R has no units, and so the number will not change if the measurement units are changed. So if we're looking at the weight of a mouse versus its tail length, and we look at the weight in ounces and the tail length in centimeters, and we say, aha, we really should measure the tail length in inches. So we change centimeters to inches. If we would recalculate R, we would get the same value. The first thing we do is we explore the data and we look at the scatter plots. So you can see the scatter plot on the left has a definite trend. It goes up from left to right. That's a positive correlation. You can see the scatter plot on the right goes down from left to right. There's a correlation there. It's a little bit stronger than the one on the left, but it's a negative because large x values are associated with small y's and vice versa. And then this scatter plot really has no pattern, and so this would be good evidence of no correlation. Not all relationships are linear. This has an R. We can calculate an R value, but R makes no sense here at all. Okay, this is an example of scatter plots. It's from a presentation that's similar to a TED Talk, and this gentleman was head of the Swedish Health Ministry, and he's got a lot of very interesting statistics.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
Think about which ones were the explanatory variables, which ones were the response variables, and look at the patterns that you saw from the graph. Now, in order to do a correlation, there are some things that have to happen. So the first one is the data needs to be paired, and it's two things that are measured about one individual, and that those are simple random sample, and it must be quantitative data. We will look in chapters 11 and 12 how we deal with qualitative data. Then we're going to look at the scatter plot to see that we're approximately straight line, and we need to identify outliers, because outliers can greatly influence our value for R, and we'll talk about why that is when we get to the definitional formula for that. Here is the list of values we need. They should look pretty familiar by now. We're going to use R for our sample correlation coefficient, and this thing that looks like a P is lowercase Greek letter rho, and that stands for our correlation coefficient for the population. Now, this is the formula that I want to talk about. This is the definitional formula. If you look on page 533 in your textbook, formula 10.1, that's a computational formula that you would use if you were going to calculate it by hand. You can see how we would use our definitional formula on page 538 in our chapter problem. But the thing I want to talk about here is we need to standardize each value. So z sub x means that's our standardized x, and z sub y is our standardized y. And so what we're going to do is we're going to multiply those together for each one of our individuals. Once we get all those products, we add those up, and then we're going to divide by the number of pairs minus 1. Now, if you want to, you can practice and you can use this formula, but it's unnecessary because we are going to use software to calculate this. How do we know if our R is statistically significant? Well, on your list of on that sheet I handed out at the beginning of the semester, I gave you there is a table called A6, and it's called Critical Values of the Pearson Correlation Coefficient R, and N is going to be the number of pairs, and then you have critical values either at the 0.05 level or at the 0.01 level. These are going to be your critical values, and if your R exceeds the absolute, if the absolute value of your R exceeds your critical value, then it's statistically significant. We can add this to our you can reject Ho-When list, and again, if the absolute value of our calculated R is greater than our critical R, we can reject Ho. Or if our p-value is less than our significance level, we can reject Ho. These rules haven't changed. We've just added R to our list of Z and T. Now, again, you need to be cautious. This is only for a linear relationship. If when you do the scatter plot there's no linear relationship, then don't even waste your time doing the math. Again, our R has to be between a -1 and a +1 inclusive. Units don't matter. R is not affected by which one's X and which one's Y. it simply measures the strength of the linear relationship. But R is very sensitive to outliers, so that's going to be one of those things that we look at when we explore the data, and we will do this graphically in a few slides. Here is our example, our shoe print length and our height. You can see this data table on page 529, and the first thing we're going to do is we're going to graph it, and you can see it's kind of linear. We start low and we go high. It does look like that we might have an outlier or an influential point here, but let's go ahead and let's continue. And here is the output that we get from Minitab, StatDisk, those are computer programs, or with TI-83 or 84 plus. I want to pause now and let's go ahead and look at how we would do this with StatCrunch. Here you can see that I entered the data. I'm simply going to go to Stat. I want to go to Regression, Simple Linear. I'm going to click, where's my X value? It is shoe print, and my Y variable is height because I want to try to predict their height from the length of their shoe print. I'm not going to do hypothesis testing right now, or predicting, so I'm just going to go ahead and do compute, and here's what I get, and I get my correlation coefficient 0.5912699. That's exactly the same as we got before. We got some other stuff here that we're going to look at later in section 10.3, but right now that's what we know. Let's use table A6, and we had 5 individuals, so our N is 5, and we want to look at, let's go ahead and do 0.05. That doesn't take as much evidence to throw out our null hypothesis, and you can see our critical value is 0.878. Our value of 0.591 is not further out in the tails than that, so this is not statistically significant. Now, according to the software, it says our p-value is 0.294, so our p-value is not less than 0.05, so again, it's not statistically significant. Remember, our critical value method and our p-value method will never disagree with each other. Here is a picture that tells us what it is. Here is our critical value. Here is our sample value. It's not further from the mean than our critical value, so it's not statistically significant. Here's another example. We had data and we found the value of R is 0.117. If we had 62 pairs, table A6 with 60 gives us a critical value of 0.254. You can see that our 0.117 is not further out in the tails than that, so it's not statistically significant. Our p-value is quite large, so again, it's not statistically significant. Our requirements were satisfied. It was a simple random sample. The scatter plot was an approximate straight line with no outliers. So again, like I said, we look at the value and it would not be beyond our critical value. Now, what we want to do here is we want to talk a little bit more about R. When we square our R value, it tells us the proportion of the variation in Y that's explained by the linear relationship between X and Y. And one of the things that we can do here is if we look at this, let's say we did 40 pairs of shoe print lengths and heights, and then the linear coefficient is 0.813. If we took that number, 0.813, and we squared it, we will get 0.661. Okay, what that means is about 66% of the variation in height is explained by the relationship between the lengths of shoe prints and heights. So that means there's about 34% of the variation that can't be explained. Now, this is where your intuition comes in. There are some things that if we can explain 2/3 of the variation, that's pretty good. But there are other things that if we can only explain 2/3 of the variation, that's not a very good estimate. And we'll talk more about situations like that in a bit. But let's talk about some common errors involving correlation. First of all, correlation is not causality. We need a lot more than a simple calculation to show that one thing causes another. When we use averages, averages suppress individual variation because remember, average data is less variable than individual data, and that could inflate any correlation coefficient. Remember back to the video when he had that large bubble that represented all of China, and when he broke it out by Shanghai, which is a very industrial westernized province, and the rural province, what happened to the wealth and the lifespan? It made a big difference from the China averages. And remember that there may be some relationship between X and Y even when we get an R of 0, because the relationship may not be 0. So again, be careful. Correlation does not imply causality. Here are some more scatter plots that show you no correlation up to a very weak correlation. This is a chart that I found when I was doing my research to give you an idea of, is it a strong, moderate, weak, or very weak relationship, just to give you some idea. And there's the website where you can go to find where I found that information. Some more examples. A husband's versus a wife's age. Usually as you have older husbands, you have older wives. And that correlation coefficient would be 0.94. Now let's just look at this, that if I gathered a lot of data, I would think about this, and I would say if I take 0.94 squared, I get 0.8836. So I could say, because of our data, about 88% of the variability in the wife's age is due to the relationship between the husband's and wife's ages. The husband's versus a wife's height. Think about it. Do you expect that correlation coefficient to be higher or lower? Well, it's lower. Although tall people tend to marry taller people, it really isn't as predictable as ages. And again, if we take 0.36 and square it, we get 0.1296. So about 13% of the variability in wife's heights is due to the relationship between the husband's and wife's heights. And think about the next one. We've got a professional golfer's putting success, the distance of the putt versus the percent success, and short putts, high success, long putts, lower success. So we're going to get a negative correlation coefficient, but it's still pretty high because It's a professional golfer. Now, we can always calculate a linear correlation coefficient, but it doesn't always mean anything. Here we have a graph of a vehicle speed versus the miles per gallon, and we calculated our correlation coefficient, and it's a negative 0.06, which is pretty small. And so you might be tempted to say there's no linear relationship between these variables, but look at it. There's a curved relationship between these. So just calculating that R and interpreting it without graphing can oftentimes be misleading. Problems. Outliers can inflate or deflate those correlations, and when we combine groups we might inappropriately mask relationships. For instance, the rural and urban provinces in China make a big difference, and those groups have different relationships when separated. Here is a picture of what we mean. Now, for each scatter plot above, notice for A that we could sketch a line and be pretty close to most of those, but our influential point up here will draw that line up away from the rest of the points. And notice here our points are grouped, and this point here is going to make that line much more definite, and it's going to make our R much higher. So both of these relationships would be much better if we would eliminate this one would be an outlier, while this one is going to be an influential point. A is going to be an outlier because it would decrease the correlation, while A decreased the correlation and B increased the correlation. Here is another example. This is per capita gross domestic product and average life expectancy for 10 countries in Western Europe. Let's look at this. Here we have our data and our life expectancy. And this is what we would get if we calculated it by hand. That's not going to be something that you're going to want to do. So let's stop and let's do this one using StatCrunch. Okay, I've already put the data into StatCrunch, and again I want to go to Stat, Regression, Simple Linear. My X variable is my GDP because I want to be able to predict life expectancy from gross domestic product. Let's do compute, and let's look at this. Now I want to show you that here is our correlation coefficient, negative 0.18. Here is our R squared, and so that's about 3% of the variation in life expectancy is due to the relationship between GDP and life expectancy. You can see our p-value down here is not very small, so I would say this is probably not statistically significant. One thing I do want to show you in StatCrunch is you'll get more than one page, and here is my fitted line, and you can see that we really don't have a strong linear relationship. This is a data set that I've used as an example, and we have this is a fossilized bird/reptile. Scientists believe that the Archaeopteryx is kind of the missing link between reptiles and birds, and they found these 5 fossilized skeletons. And so we take their femur length versus their humerus length. Remember, the femur is the long bone in the leg and the humerus is the long bone in the arm. And we want to see if there's a relationship between the femur length and the humerus length to show that these are fossils of the same species. And what we would do is to do this is we would set this up and we would calculate the mean, the standard deviation of x, the standard deviation of y, the mean of y, and that's when we would plug it into that calculation formula. But we don't need to do that. We can use StatCrunch. So here again, I have my data already into StatCrunch, and I'm going to go Stat, Regression, Simple Linear. My x variable is the femur, and the y variable is the humerus, and I'm simply going to do Calculate, Compute, and here I get my data, and you can see that my correlation coefficient is 0.994. My p-value is 0.0005, which is very small, and so I have a strong positive correlation coefficient. My p-value is very small, so this is probably a statistically significant correlation. Another thing I want to point out is if we square 0.994, we get 0.988, and so what this says is that more than 98, almost 99% of the variation in the arm bone is due with its relationship with the length of the leg bone. And again, we can look at the scatter plot and you can see these are very close to being linear. Now that we've looked at how we calculate that correlation coefficient, let's go ahead and do a formal hypothesis test. So we want to see if there's a significant linear correlation between two variables. And so again, you know the notation. N is the number of pairs, R is the linear correlation coefficient for a sample, and rho is the linear correlation coefficient for the population. So we need to test the requirements. The data need to be paired. We must have checked out the scatter plot. It's appropriate to use a straight line pattern, and any outliers are removed. And so then what we're going to do is we are going to look at this, and what we have here is here is our step 1. We're going to set alpha equal to 0.05. Then we're going to calculate our test statistic R. Step 3, remember, is our summary of data. You might want to put the data table there. Step 4 is actually calculating the test statistic, and we would use that from StatCrunch, find our p-value, and then remember that step 5 would be reject or fail to reject, and then step 6 is going to be our summary statement. So again, if our R is greater than our critical value, the absolute value of R is greater than the critical value, we can reject HO. If our R is less than or equal to our critical value, then we fail to reject. But we're going to look at p-values, so let's take our shoe example, our footprint example, and remember that our R is 0.591. Let's go ahead and conduct a test at 0.05. And so here is our step 1. Our test statistic is 0.591. It is not bigger than our critical value, so it's not statistically significant. So we fail to reject the null hypothesis, and these data suggest there's not evidence to support the claim of linear correlation. Now, when you have such a small sample, this would not really be publishable information. You might be able to publish a paper that says, my small sample suggests this, but I would recommend another study with more individuals. Now, here is how we would calculate a t-statistic from our R, but again, we don't need to. Our p-value in this case was 0.20. Here is our t-statistic, 1.269. We can calculate a p-value of around 0.2 from our table, but technology says it's 0.2937, not less than 0.05, so we fail to reject our null hypothesis, and there's not enough evidence to support the claim of a linear correlation between the shoe print length and the height. When we do tests, we might need to do one-tailed test or two-tailed test, in that this would be, we're claiming a negative correlation. So that would be a left-tailed test. Our R is less than 0. Or we might do a positive correlation. R is greater than 0. Or we might do the two-tailed test that R is just not 0. We don't care if it's positive or negative. We just are interested that it's not 0. Now again, we can use the p-value method as we did earlier. Let's just take a minute and go back to StatCrunch, and I wanted to show you that we were testing the slope, which is this line right here. And notice that we used a two-tailed test and not equal to. You will never test the intercept. That really doesn't have anything to do with anything. Here is the t-statistic, just like they found on the slide, and here is our p-value, just as they found on the slide. So I hope that kind of helps pair up where we would find these things on our StatCrunch printout.